Hey, what's up, Chem peeps? Who's ready for some free response? Ooh, a picture. Each of the 3 beakers contains 25.0 milliliters of a 0.100 molar solution of HCl, NH3, or NH4Cl as shown above. Boom! Each solution is at 25 degrees Celsius. Part A. Determine the pH of the solution in beaker 1. Justify your answer. Alright, first thing we want to do is take a look at beaker 1 and recognize that it contains hydrochloric acid, a strong acid. Therefore, whatever the concentration of the acid is, that will also be the concentration of the hydrogen ion because it is a strong acid and completely ionizes. So, pH equals negative log hydronium ion. Boom. We're simply going to plug in the concentration for the hydrogen ion. Boom. And then jump to your calculator if you need to. Negative log 0.100, enter. Now be careful here. Easy to lose a point when it comes to sig figs and logarithms. pH to the correct number of sig figs is 1.000. Remember, however many total sig figs you have in the value that you're taking the log of is the number of digits that come after the decimal. Boom, 1 point. Done. Part B. In beaker 2, the reaction NH3 plus H2O is in equilibrium with ammonium ion and hydroxide ion occurs. The value of Kb for NH3 is 1.8 times 10 to the minus 5 at 25 degrees Celsius. Subpart I. Write the Kb expression for the reaction of NH3 with water. Easy. Kb equals concentration of ammonium ion times concentration hydroxide ion over concentration ammonia. Done. 1 point. Remember, we're not including water because we don't include pure liquids in our equilibrium constant expressions. Subpart 2. Calculate the hydroxide ion concentration in the solution in beaker 2. Alright, as we scroll back up and take a look at beaker 2, recognize that in beaker 2, we have a weak base, ammonia. Now we're provided with the reaction for ammonia with water, but I'm going to rewrite it here beneath subpart II. Boom! Because it's a weak base, it's not going to completely form all this product. We've got to set up an ice table. Boom. Recall that we're told the initial concentration of the ammonia is 0.100 molar. I'm going to drop my water, 0 for ammonium ion, 0 for hydroxide ion. My change, minus x, plus x, plus x. At equilibrium, 0.100 minus x, x, x. We've just written the expression for Kb in subpart I, so now we just need to plug in our equilibrium concentrations that we just determined from our ice table. And plug in the value of Kb that we're given in part B. 1.8 times 10 to the minus 5 equals x times x over 0.100 minus x. All right, to make our life a little easier, we're going to make the x's small approximation, but it's free response. I'm going to make sure that I spell that out. X is small approximation is valid because initial concentration of ammonia and Kb differ by a factor greater than 1,000. So important. Be clear about that. That simplifies our Kb expression to 1.8 times 10 to the minus 5 equals x squared over 0.100. Calculator. Parentheses 1.8 second e negative 5 close parentheses times 0.1 enter second square root second answer. X equals 1.3 times 10 to the minus 3 molar. That is my hydroxide ion concentration. Boom. Now, this is worth 2 points. You get 1 point for the correct setup, indicating that X is small approximation, and 1 point for the correct answer with units. Part C. In beaker 3, the reaction ammonium ion plus water is in equilibrium with ammonia and hydronium ion occurs. Subpart I. Calculate the value of Ka for ammonium ion at 25 degrees Celsius. Oh man, this is kind of tricky. How am I supposed to determine the value for Ka? I'm not given an equilibrium concentration. Should I use an ice table? Should I give up? Well, like many free responses, the answer lies in earlier parts of the question. Recognize that ammonium ion is the conjugate acid to ammonia, the weak base that we were just working with in part B. And we're told the value of Kb for ammonia. And because ammonium ion is its conjugate acid, it's really important that we remember this relationship that exists between Ka and Kb. Boom. So important. Can't forget it, it's on your formula chart. Let's jump back up and grab the value for Kb from part B, which is 1.8 times 10 to the minus 5. Plug it into this equation. Boom. Divide each side by our Kb. Jump to our calculator. Parentheses 1.0, second E, negative 14, close parentheses, divided by parentheses 1.8, second E, negative 5, close parentheses, answer. Ka equals 5.6 times 10 to the minus 10. Boom. This part is a common question that you want to be comfortable with. Many times we're moving at 1,000,000 miles an hour trying to work through these free response questions. Always think about your trusty formula chart to get you out of these sticky situations. Subpart II. The contents of beaker 2 are poured into beaker 3 and the resulting solution is stirred. Assume the volumes are additive. Calculate the pH of the resulting solution. All right, let's go up here and refresh our memories about what's going on with beaker 2 and beaker 3. All right, so in beaker 3, we've got our weak acid ammonium ion, and we're going to be adding to that its conjugate base, NH3, an equivalent amount of our conjugate base, NH3. So weak acid conjugate base, you guessed it, buffer. And an amazing buffer, because we're mixing together equal concentrations and equal volumes of a weak acid and conjugate base, which is exactly what we want to do to make an ideal buffer. All right, so the first thing I'm going to do that's not necessary but helpful when you're trying to understand what's going on here, I'm going to write out the equation that represents the buffer solution that is made upon mixing these two beakers together. Boom. And with any buffer problem, you always want to think about the Ka expression for that buffer solution. Boom. And importantly, when we're working with pH of buffer systems, let's think about how we can rearrange this Ka expression to solve for the hydronium ion concentration. We get, boom, hydronium ion concentration equals Ka times our weak acid ammonium ion over our weak base ammonia. We know that we have equal concentrations of ammonium ion and ammonia. So let's be clear about that for our AP reader. In resulting solution, the concentration of ammonium ion equals the concentration of ammonia. Now what that does for us, because these two values are the same, ammonium ion concentration and ammonia concentration, anything divided by itself, whatever it is just going to drop out of the calculation because anything divided by itself is 1. Which means then, therefore, hydronium ion concentration equals Ka, which we determined up here in part C to be 5.6 times 10 to the minus 10. Boom. To get pH, remember we're going to take the negative log of the hydronium ion concentration. pH is equal to negative log 5.6 times 10 to the minus 10. Calculator. Negative log, second answer. So our pH equals 9.26. Boom. All right, we're in the home stretch here, part D for almost done. The contents of beaker 1 are poured into the solution made in part C subpart II. The resulting solution is stirred. Assume the volumes are additive. Subpart I. Is the resulting solution an effective buffer? Justify your answer. All right, let's do this. The resulting solution is not an effective buffer. Okay, we've answered it. Now let's justify. Virtually all of the NH3, the conjugate base, will neutralize all of the added strong acid, according to the following equation. NH3 reacting with the hydronium ion, right, the H part of our HCl, to form ammonium ion, its conjugate acid, and water. That's why it's so important to be comfortable with how a buffer works and the reactions that the weak acid or conjugate base undergo in order to neutralize added strong acid or base. All right, I'm gonna keep going here. Mostly NH4 plus remains after mixing because only one part of the weak acid conjugate base pair remains, the solution cannot buffer against both strong acid and base, which remember is one of the characteristics of an ideal or effective buffer, being able to effectively neutralize at its strong acid or strong base. And it was a great buffer to start, right? We had equal concentrations of ammonium ion and ammonia, but by adding all that strong acid, we used up all of that ammonia. So it was a great buffer. We've just exceeded its buffer capacity. And at this point, the resulting solution is not going to make a good buffer. All right, and that brings us to subpart II. Calculate the final ammonium ion concentration in the resulting solution at 25 degrees Celsius. Okay, so originally in Beaker 3, we have 25 mils of 0.1 molar ammonium ion. Beaker 3, I'm going to use my molarity equation to solve for the number of moles of ammonium ion that were originally in that beaker number 3. 0.00250 moles ammonium ion. This was originally what we had. And then think about what we did up here in part C and D. First, what we did is we added a bunch of this conjugate base into beaker 3, creating a really amazing buffer. But then we added this hydrochloric acid into that beaker and realized that the ammonia neutralized all of that added acid, forming additional ammonium ion. So beaker 2, 0.100 molar equals X over 0.0250 liters equals 0.00250 moles of NH3. But think of this equation: for every 1 mole of NH3, we're going to make 1 mole of NH4 for every mole of hydronium ion or mole of strong acid that we add. So I'm going to go mole NH3, mole ammonium. That's a 1-to-1 relationship, which will give me another 0.00250 moles NH4 plus. You know what? Let me be a little more clear about this. Beaker 3 initially, and I'll say Beaker 2 after combined with Beaker 1. Super clear. So after I've mixed all these beakers together, I've got my 0.0250 moles ammonium ion originally from Beaker 3. And then after my strong acid reacts with the conjugate base, I'm going to get another 0.0250 moles of ammonium ion in that beaker. So total, I have 0.00250 mole plus 0.0025 mole NH4 plus, and I added together all 3 of those beakers. And remember, we want concentration, so it's going to be number of moles over the total volume, which is 25 mils plus 25 mils plus 25 mils. I'm a genius, don't even need a calculator. 0.0050 moles over 0.0750 liters, which equals, I'm going to jump to the calculator to make sure I get my zeros right. 0.0050 divided by 0.0750 answer. 0.0667 molar ammonium ion. Boom. Done.